Welcome back everyone. In this lecture we will complete the proof of Schur orthogonality relations. So, let us recall the preparatory lemma that we have stated in the last class. So, here is the lemma. So, we take phi and rho to be unitary representations of G. So, let us say the degree of phi to be n and then degree of rho to be m, and then we looked at what happens to this EKI hashtag, and then we observed that the LJth entry of this EKI hashtag is going to be given by this inner product between the matrix coefficients phi ij and rho kl, and this is true for all ij and kl. Okay, so recall that for given aij, so the A star is given by A transpose bar. So, that means that A star, the ijth entry is going to be aj I bar. Now, if given matrix is unitary, so then we can observe that A inverse is going to be A star. So, in particularly since rho is unitary, so here is the proof, since rho g is unitary, so we have rho g inverse, which is exactly rho g of inverse. So, then this is exactly rho g star. So, that implies that if we compute rho L k of G inverse, that is going to be exactly rho k L G bar. So, now let us compute this EKI hashtag and then L j. So, this is going to be, so recall the definition of T hashtag, which is exactly 1 divided by the cardinality of G summation. So, we take all possible rho G inverse T phi G, where G runs over G. So, that means this EKI hashtag is going to be 1 divided by the cardinality of G summation rho G inverse EKI phi G, and then we want to look at the LJth entry of that. So, we will just compute it, but we have already seen that how to compute LJth entry of AXB, where x is EKI. So, if we recall what is this LJth entry, then you can easily see that this is exactly 1 divided by the cardinality of G summation G in G rho L k of G inverse phi I j of G. But we can substitute this term as rho k L of G bar. So, then if you do that, then this is exactly equal to 1 divided by the cardinality of G summation rho k L G of bar and then phi I j of G, G in G, that is what we get. Now, if you think about it, this is exactly the definition of the inner product phi I j rho k L. So, then we get this is exactly equal to phi I j rho k L. So, that actually tells us that the LJth entry of this EKI hashtag is nothing but the inner product phi I j EKI. So, now we are actually indeed ready to prove the Schur's orthogonality relation. So, recall that this relation between this hashtag and this matrix coefficients. So, that is what going to help us in order to prove this orthogonality relation. So, we have actually viewed this projection map as a map from this m by n matrices to this m by n matrices. So, now since we have assumed that both phi and rho are irreducible representations. So, since phi and rho are, so they are assumed to be inequivalent irreducible unitary representations of G. So, because of this we can see that the image of this P, which is nothing but the home space between V comma W. So, that is going to be 0. So, that means this EKI hashtag, so that is supposed to be 0, because the image of P itself is 0, which is actually the map T goes to T hashtag. So, that means we get that all Ljth entry of this EKI hashtag is 0, but we just seen that this is nothing but the inner product phi ij rho kl. So, that means this phi ij rho kl, they are all orthogonal to each other. So, that is the first property of the orthogonality relation, that phi ij and rho kl. So, that is exactly 0 for all ij and kl. So, where we assume that phi and rho given irreducible inequivalent unitary representations of G. So, now let us actually work it out what happens to the second orthogonality relation. Again, that also follows immediately from Schur's lemma. So, recall that if phi equal to rho, so then this T hashtag is going to be multiple of identity, and we also know what will be that constant term. So, that is exactly going to be given by the trace of T divided by the degree of the representation. So, now using this result we can compute what happens to this EKI hashtag. So, recall that. So, this EKI hashtag is going to be exactly equal to the trace of EKI divided by the degree of the representation, which is exactly n times identity. So, identity on the space V. So, now from this equality we can actually compute what will be the Ljth coefficient. So, on the other hand we have this EKI hashtag Ljth coefficient is given by the inner product phi ij phi kl. So, this is already we have observed. So, now let us put them together and then conclude something about the inner product. So, let us assume that L is not equal to j. So, if L is not equal to j, so then you can easily see that the Ljth entry of this matrix, identity matrix. So, that is going to be 0. So, then the Ljth entry of this identity matrix is going to be 0. So, that means this EKI hashtag Lj is supposed to be 0, and that would imply that the inner product phi ij phi k l is going to be 0. And now, let us look at what happens when I is not equal to k. So, now suppose I is not equal to k. So, then it is immediate that the trace of E k I is 0, because E k I, the 1 will appear at the k ith entry, which is not on the diagonal. So, that forces that this is 0. So, even in this case you can see that, so this entire E k I hashtag is going to be 0. That means E k I hashtag L j is going to be 0. So, that means the inner product phi I j phi k l is going to be 0. So, the only case that remains now, L equal to j and I equal to k. So, that is the only case remains. So, in this case you can see that again, if we go back to the inner product phi I j phi k l. So, what we get? So, the inner product phi I j, which is same as the inner product phi I j phi I j. So, which is given by E I hashtag the entry LL. So, that is again given by, so we are looking at the LLth entry here in this term. So, that means, so this is exactly equal to the trace of E I divided by the degree of the representation times the LLth entry of the identity matrix, which is exactly 1. So, then this gives exactly the trace of E I divided by n, but the trace of E I is going to be 1. So, this is exactly gives us 1 by n. So, that means the inner product phi I j is exactly given by 1 by n, and that actually proves the Schur's orthogonality relations. So, let me just state it again. So, here is the result that we proved, the Schur's orthogonality relations, and it is such an important result, and we will be able to conclude so many things about the representation space using this. So, we assume that both phi and rho are the irreducible, inequivalent, unitary representations of G, and it is not indeed a big assumption. Only thing is we want to actually make sure that phi and rho are irreducible. Then up to equivalence you can always choose unitary representations from the equivalence class of this phi and rho. So, then we have the following orthogonality relations. The first relations phi I j rho k l. So, they are going to be orthogonal to each other, and then when we compute this phi I j and rho k l, sorry, phi k l. So, this is going to be exactly 1 by n if I equal to k and j equal to l and 0 otherwise. So, basically we could see that if we consider this projection operator, basically the projection operator is what possesses all the information about this inner product phi I j rho k l. So, if you recall what we did, so we actually said that this E k I hashtag and LJth entry of that is given by this inner product phi I j rho k l. But what is this? This is exactly the Lj comma k entry of the matrix P with respect to the standard basis. So, the P is the projection operator which is given by t goes to t hashtag. So, when we compute the matrix of this P with respect to the standard basis and then look at its Lj comma k I entry. So, that is exactly given by this inner product phi I j rho k L, and the orthogonality relation says, so those coefficients they have some important information. So, this orthogonality relations explicitly describes what the coefficients of the matrix of P. So, that is the another interpretation of this Schur orthogonality relation. Okay, so, let us actually prove some of the important applications of this result. So, first of all, what one can do, one can actually reprove the orthogonality of the irreducible characters using the orthogonality relations of matrix coefficients. Maybe I will leave that as exercise to you, you can try to actually prove. So, the exercise, so use Schur orthogonality relations of this matrix coefficients to prove the orthogonality of the first orthogonality relation. So, the first orthogonality relation talks about the orthogonality of irreducible characters. So, this is something you can obtain directly using the Schur orthogonality relations of matrix coefficients. Anyway, that is just a computation, I will leave it to you to check. But now you can see that these matrix coefficients they are all actually elements of this CG. So, now since they form orthogonal set, using that orthogonal set we can actually get easily orthonormal set. So, as an immediate corollary we can see that if we take phi to be unitary irreducible representation. So, this is irreducible plus unitary representation of G. So, then it is immediate that if we take the square root of n phi I j. So, for all I j runs over from 1 to n. So, this is going to be orthonormal set. So, this form on orthonormal set. And this is immediate from the orthogonality relation, because the inner product between phi I j is going to be 1 by n. So, basically we adjust the scalar so that we get 1. So, in particularly you can see that they form a linearly independent set inside your space of complex value functions from G. So, now again as an immediate corollary, if we take inequivalent irreducible representations, we already told that inequivalent, the number of inequivalent irreducible representations will be finite. So, if we list them all, then we will be able to actually get some bound on that number of irreducible inequivalent representations. So, here is the main theorem. So, let G be a finite group, and what we are going to do, we are going to list all the inequivalent irreducible representations. So, this is the complete set of representatives of the equivalence classes of irreducible representations. And we just denote di by the degree of these representations. So, then what one can prove? One can prove that if we take this square root of this dk and then phi I j k. So, these are all the matrix coefficients of all these irreducible representations, and note that this k varies over from 1 to s, and depending upon k this I j's varies over from 1 to dk, and these d1 square plus etc. d s square set of elements, they form an orthonormal subset of C G. So, this is on orthonormal subset of C G. So, in particularly, so since we know the dimension of this C G, we can see that since the d I squares are all non-zero, so then S is going to be less than or equal to d 1 square etc. d s square, and then this sum is going to be the cardinality of this set. So, the cardinality of this set is exactly d 1 square plus etc. d s square. So, this is going to be at most the dimension of C G, which is exactly the cardinality of G. So, as an immediate corollary, we get the number of irreducible inequivalent representations will be at most cardinality of G, but anyway we already proved that that is going to be at most the number of conjugacy classes of G. So, this is indeed weaker, but this is something interesting that S is sorry, the sum of this d I square is going to be at most the cardinality of G. And this is again immediately follows from the Schur orthogonality relations, because whenever we take inequivalent irreducible representations phi I j and rho k l, they are going to be orthogonal to each other. So, then this theorem is indeed immediate corollary of Schur's orthogonality relations. Okay, so indeed what we will prove later that this set is going to form a basis for C G. So, this is not just going to be orthonormal subset. So, it is indeed a basis of C G, but the way we prove it is a basis, so we actually like directly show that the sum of this d I square is going to be exactly equal to the cardinality of G. Okay, so this actually allows us to set up some notations. So, I already promised earlier that we will prove that the characters actually determines the representations. So, what does it mean? So, whenever we have equivalence of representations, then we immediately got that the corresponding characters will be same. The character of rho and character of phi, they are going to be same. But what we want to prove now, the converse is also true, like whenever the characters are same, then the corresponding representations must be equivalent. So, this is again very important observation. So, how we can prove this? So, for that let us actually fix some notation. So, we call this V direct sum M to be the direct sum of V M copies of direct sum of V. So, this is, and similarly the representation like direct sum of M copies of phi is denoted by phi power direct sum of M, phi direct sum etc. direct sum phi. So, this is the notation that we will use. So, now note that using this complete reducibility. So, using the complete reducibility, we know that any given finite dimensional representation can be written as direct sum of irreducible representations, but from our earlier theorems we know that the number of inequivalent irreducible representations, that is going to be finite. So, let us call this V1 etc. Vs to be the inequivalent irreducible representations of G. Note that each equivalence class has one unitary irreducible. So, we can pick any representative from each isomorphism class, no issue. So, now using the complete reducibility, we can see that this V can be written as direct sum of these inequivalent irreducible representations. So, this is the complete class, this is the complete set of inequivalent irreducible representations. So, in particularly V, you can write it as V1 direct sum M1 direct sum etc. direct sum Vs direct sum Ms. So, these Mis, they are called multiplicity of Vi inside V. So, now in order to prove the uniqueness, so we need to actually prove that these multiplicities do not depend upon these multiplicities, they only depend upon the isomorphism class, and that is actually immediate using the property that this the respective characters, they are indeed linearly independent. So, you can see that the character of this V is going to be the character of V1 M1 times plus etc. plus Ms times the character of Vs. So, now from this we can see that suppose if we have some other way of decomposing this V into direct sum of irreducible representations, then we might have different set of multiplicities, but then that would imply immediately that the chi V is going to be given by M1 dash chi V1 plus etc. plus Ms dash chi Vs. But since the character does not change under the isomorphisms, so that means this is going to be exactly equal to M1 chi V1 plus etc. plus Ms chi Vs, and since the irreducible characters, they are linearly independent. So, that would imply that immediately the multiplicity is supposed to match. So, that means this M1 etc. M1 equal to M1 dash etc. Ms equal to Ms dash. So, that means the way we decompose V into direct sum of irreducible representations, so that is unique up to permutation and isomorphism. And in particularly if we have the character of two representations are equal, so then we can see that the corresponding representation will be decomposed into direct sum of these irreducible representations. So, then the multiplicities of these Vi appearing in both V and W, they must be equal. Again that will follow from the linearly independence of these characters. So, let us write V and W as follows, then that would imply that chi rho is same as M1 chi V1 plus etc. plus Ms chi Vs, which is same as N1 chi V1 plus etc. plus Ns chi Vs, as this is same as chi rho is same as chi phi. But since again using the linearly independence, using again linearly independence, we get that this Mi should be equal to Ni for all I. So, that means these representations must be isomorphic, because these multiplicities indeed determine the representation, and that means these representations are indeed determined by the characters, because the characters indeed determines the multiplicities. Okay, so as I promised, I have proved the uniqueness of these multiplicities, and the characters, they determine the representation. Both follows from the single stone, that the irreducible characters, they form a linearly independent set. So, now if we are interested in computing these multiplicities, that also can be actually computed using the characters. So, if we write V as V1 direct sum M1 plus etcetera direct sum V as direct sum MS, then it is immediate that the character chi V, when we compute it with the character chi I, where chi I is nothing but chi Vi. So, this is going to be exactly equal to Mi. So, this follows from the orthogonality relations of these irreducible characters, because chi I, chi j, so this is exactly given by delta ij. So, now if we compute this chi v and chi I, you can see that this is exactly equal to summation mj chi j chi I, but using the linearity in the first variable, we can see that this is exactly equal to summation chi j chi I with the coefficient mj, j range from 1 to s. But now using this orthogonality relations, you can see that this is exactly given by Mi. So, by computing the characters and then its inner product with the irreducible characters, one will be able to compute the multiplicity of this irreducible representation that occurs in V. So, this gives us a way of decomposing V into direct sum of irreducible representations. So, basically the characters, they possess all the informations about the representation. So, if we are interested in decomposing the representations, so then we need to find out all possible irreducible representations up to isomorphisms. Then once we have listed all the irreducible representations up to isomorphism, then we can find out their characters. So, then given any representation, we can just simply compute its character, assuming that we could do, then we can compute these inner products. So, then using that, we will be able to say what multiplicity of given irreducible representation inside given representation V. So, that actually tells us one can compute the decomposition using computing things about characters. And this also actually gives as an immediate corollary some irreducibility check for the given representation. And it is easy to see that a representation is irreducible if and only if in terms of the character the inner product has to be 1, because we already seen that the inner product is always this Mi. And not only that, you can also actually give the character value chi rho the inner product. So, this is going to be using the orthogonality relation. You can see that this is going to be exactly the sum of Mi square. Again, we can use the orthogonality relations to prove these corollaries. Okay, so I will stop here. So, this is all about the orthogonality relations of characters. So, later, like I said, I want to give actually more conceptual proof of all these results in terms of representation theory. So, for that purpose, we need to develop the tensor products and so on. So, that we will do in later classes. Okay, I will stop here. Thanks.